3 resource-efficient food alternatives for deep space missions. Presented by the Alliance to Feed Everyone in Disasters and Space, the ALLFEDS. At $10,000 per pound, launching food into space is expensive. But relying on prepackaged food, as is normally done, limits the length of time the space mission can last. To solve this, many researchers have proposed using artificial light to grow microalgae or vegetables, but this is energy intensive, which can lead to significantly greater mission costs. We have identified 3 food sources that are significantly more efficient in their use of mass than prepackaged food and artificial light. For the same amount of mass at launch, these options could potentially increase the possible mission time tenfold, from 2 years to over 20 years. Our first solution is single-cell protein. Using continuous fermentation technology, microorganisms are fed hydrogen and oxygen obtained from water electrolysis, carbon dioxide from the air, and some extra nutrients they need to grow. The microorganisms are taken out of the reactor and dried to a powder via centrifugation and spray drying. This produces a high-quality, protein-rich food while also recycling the carbon dioxide that the astronauts exhale into oxygen again. Our second solution is nonbiological synthesis. Carbon dioxide and water are converted into edible glycerol, also known as glycerin, via an integrated chemical process composed of electrochemical, catalytic, and hydrogenation reactors, while byproducts are burned to be recycled and reused in the process all over again. Finally, our third solution is microbial electrosynthesis, which uses special microbes capable of eating electricity and carbon dioxide to produce acetic acid, also known as vinegar. After removing the microbes, the vinegar is ready for the astronauts to consume. These foods could be combined into a nutritious, palatable diet, potentially with the help of supplements, flavors, and perhaps a small amount of prepackaged food. Operations, shutdown, and cleaning would only require a small amount of crew time. If production needs to be restarted, re-inoculation protocols are used to bring the equipment back online using backup starter cultures. These foods have great potential for Earth as well. In fact, the reason we started studying and developing these solutions is because they could help civilization survive a global catastrophe. Humanity is unprepared for global catastrophic risks, such as a supervolcanic eruption, that could obscure sunlight and cause agricultural collapse. Because the food sources we propose are completely independent of traditional agriculture, these solutions can help prevent global starvation in these scenarios. Moreover, because the main inputs are carbon dioxide, water, and energy, these solutions could be used to produce food sustainably while also acting as negative emissions technologies. That means these solutions can prevent more carbon dioxide from ending up in the atmosphere, while also enabling us to feed more people around the world while using less water and land.